So this leads us into our t-test and t-distributions. I'm just kind of quick review is that our t-distribution, we saw it before, it's kind of like our normal distribution. So we'll talk about t-tests in a second. T-tests are basically just like z-tests, like your z-statistic, but instead of using the normal distribution, which is what the z-test is, the t-test basically allows for the t-distribution. And then we saw like why this one might be useful, I think, last time. And so just know that that's why we're using a t-statistic, is that we can use it on things that are not necessarily normal. We can do a sample of means, for example. We can actually test against this. So what's interesting about this, though, is that your t-distribution, it shouldn't be a t-distribution. It's a t-distributions. It's many different kinds depending on the degrees of freedom. Basically, how much more data you have. If you have more data, your degrees of freedom is higher. Okay. So I just kind of remind you guys what this t-test looks like. Our t-distribution. So our t-test, again, is kind of similar to our z-test. Our t-statistic gives us a summary of this data. And it's, what's it called? We use the t-statistic and use the t-distribution by proxy to reject the null hypothesis. So essentially what we're saying is that like if it crosses this threshold, you know, we can reject our null hypothesis. You always want to pick your alpha value before performing this test. So basically at the end of this thing, you'll first pick up your alpha values, like, well, we'll only accept this amount of weirdness, right? With this alpha, this critical value. And then say, okay, now we're going to perform the test with our t-test, calculate the t-statistic, and we'll compare it with our alpha value. So I want to emphasize this really important because most people this will help you prevent saying things are significant when they really aren't, okay? So a couple of things to assume on our t-tests. We have to make sure our data actually comes from is independent from each other. So data doesn't affect each other. They have to be randomly sampled, right? So that means we're making sure that we're picking out not just one set of people or one set of members for the sample. We're randomly sampling. We're getting a random sample. We're picking out outliers. So sometimes you'll get people who are on this weird end of the spectrum, but a lot of times you'll also get that for the low end of the spectrum. So hopefully you kind of balance itself out. And we assume that the population data is likely normally distributed. Note that we can kind of get around this by basically taking a mean of means, a mean of sample means, right? So just know that basically we are assuming that there is a normal distribution in the population, okay? So this leads us into steps for the t-tests, okay? And again, this is much more, I would say, going through the curriculum, walking through that part and seeing like how you perform this test is really useful, but I'm gonna give you like the broad strokes of what this looks like. So the first thing you wanna do is make sure you get your question, say, what are you testing for? This will determine your null hypothesis, your alternative hypothesis. You should write these down, right? Make it very clear what you're trying to test against, okay? Then determine your significant value. Usually a good go-to is 0.05. It doesn't necessarily have to be. It depends on your situation. But for the most part, 0.05 is pretty standard. Essentially, you can give it like a 5%. Sometimes you'll get lower. For example, another common one is 0.01. You usually won't get very higher, like 0.10 is a pretty wide acceptance. In that sense, you probably don't want something that large. In that case, you probably should go back and maybe you need to fine tune exactly what thing you should be looking for. Okay, and then after you basically get your null hypothesis, your alternative hypothesis, you have your significant value all set, you're ready to actually do something with the data itself. So the first thing you're going to do is get your t-statistic, and basically this is saying how many your mean is. Your sample mean is different from our population mean. And this is calculated through here. What's nice is that in Python, we can actually use our stats package to essentially just calculate the statistic for us. But for the most part, it's relatively simple to calculate this ourselves. It's basically our average of our sample mean subtracted from the mean, the population mean right here. And this is kind of like our expected population mean. So what we expect the population mean to actually be. And this lowercase s right here, and it's kind of small right now, but that lowercase s is the standard deviation of that sample. So basically saying, for the sample that I grab, what is the standard deviation within that sample? And this basically tells us how many standard deviations or sample deviations we are from the population mean. or the expected population mean, okay? And so the idea here is that we want to see, is our sample actually different from the full population? And this full population might be, for example, the control group. So our control group is representative of the population, and our sample usually is something as the experimental group. So if, in like terms for like medical stuff, if you imagine like testing a new drug out, you would get a sample of people who don't take the drug, okay, and a sample of people who do take the drug. And you want to see, let's say, for example, this drug is supposed to lower cholesterol. It's like, well, we know from the control group that should be what the population mean is, essentially, right? Say, okay, like what do we have from this group right here? This is what it should be, the control. And then we have the drug and say, does the drug actually change how, change the let's say cholesterol, right? How different, or is it different enough from the control group? And that's essentially what we're showing right here. Okay. So once we have that our t statistic from our sample, right, we can then find our, we want to find our critical t value. And so this is basically representing where we are in, what's it called? Essentially our p-value for our t distribution. And so again, this is our distribution here. And you can imagine, or you can not imagine, is that back in the day, if anyone's done like statistics back in like high school in particular, you might be recognize this t-chart here, which basically you have to find your degrees of freedom and then say, okay, what's my p-value, my significance value? This is what this top part is right here. So 0.25, that's pretty high. Usually you'd be about right here. Say, okay, well, I had, let's say, 30 members, right? I'll just count from here. And we can see here, we go across and say, okay, our significance value of 0.05, and you can drop it down and you say, okay, that means my t statistic should be 2.75. And I want to see, or this is our t critical value, and say, okay, that's my critical value for the t distribution for my sample. And then you would compare that value with your t statistic. And your t statistic comes from your sample, okay? So hopefully that kind of, I know there's a lot of like statistic, distribution value, critical value, all these things. Basically, this is your critical value, what you're going to compare with your actual sample, which is comes from your statistic comes from your sample, okay? So what's nice though is that you don't have to use this chart. We have computers, right? We can basically calculate this. And for the record, the reason why this exists, or what this is, essentially it's an area underneath the curve. But we can have a computer determine that for us, so we don't have to look it up in a chart ourselves, okay? The reason why I use this in high school is because they don't want you to calculate the area underneath that. They don't want you to do that whole numbers. Note, as you increase the degrees of freedom, basically your sample has more and more points, your critical value gets smaller and smaller and smaller up to a certain point. So you can see here, if I only have like, 5 members in here, you need a much higher critical value to get within that 0.05 or 0.005. Oh, I guess I'm going right here. This is what we normally would look at. So this is basically saying, okay, like, what would be acceptable for you to do? Okay. So once you have your t critical value, you compare it with your statistic. And basically you say, okay, if your t value, depending if you're doing a 1 sample test or a 2 sample test, basically if your t value, let's say, is greater, your t statistic is greater than, is greater than your t critical value, okay, then you can say, okay, we can reject the null hypothesis, okay? If it's bigger or smaller in this case, if you're looking at this part, if your t statistic falls over on this side, then you're like, well, that could have just been random chance. Maybe we can't accept it in this case. So this kind of helps, hopefully this kind of helps you figure out, like, okay, like where we're looking at. This right here, this is why our critical t value will change depending on the degrees of freedom. Basically, it depends on this different shape that we have, okay? This is what we call a 1 sample t-test, right? So we have our one tail. Our one tail right here, basically, it's like, okay, like we're only looking at if it's greater than a certain value. If you wanted something that is essentially, well, I just want to know if it's different. So maybe you expect this drug to either increase heart disease or cholesterol or decrease cholesterol, and you want to know, is there a difference? Like that's the big thing. You would actually have a 2 tail where you would look on both sides of this distribution. Okay, so kind of looking at this, what scenario would have. So this 1 sample, which is what this is representing, do Snicker bars actually weigh less than 120 grams? It says on the package. So I'll put, just to make this kind of fit better, way more than 120 grams. So you can imagine on this scale right here, it's like, okay, like how, if we take our sample, let's say, for example, we get some special Snickers bars or something like that. And we're like, oh, we want to see, are these Snicker bars weigh actually more than the normal, what's it called? The normal Snickers bar? What can we, like, can we test that out? This is what we would see, like, oh, our t value is, our t critical, sorry, our t statistic is greater than our t critical value, okay? So kind of fun thing is that I said 120 grams here, and that's because I'm assuming basically the mean here, that is the mu. Does anyone got to guess like what, like, well, okay, maybe I'm kind of going too far on this, but like I said, like sometimes you don't know what the population mean is. Sometimes you can kind of determine what the population mean is. So our control here, our t statistic could just simply, or our control group can just be, what does the corporation say how much these Snicker bars should weigh? Well, they say it should be 120 grams. And so if you basically take a large enough sample and you test it and you say, whoa, like this does not weigh, like it's significantly different from 120 grams, then maybe, basically they're lying, or they're, trying to cheat a little bit and say, well, it's 120 grams, but really it's like 110. This is where you can basically use your hypothesis test to say, oh, there is a significance. A two sample one, so this is like, if it's like, oh, it's more than, is that if you want to see if there is an effect. So not just like, is it a good effect or a bad effect, just like, is there any effect at all? This might be where you use a two sample. So in this case, just know that essentially what you'll do is that t critical value gets split in two. So basically it's that it's easier to basically prove that there is an effect, but you should be careful about that. Basically know that what situation you're talking about. If you are looking to see if it's more than, you should only test for more than. Don't try to readjust your test to make your critical value work out, because then you start getting some weird results. Essentially, you're doing something called p-hacking, where you're essentially trying to tweak your thing until it works out well. Okay. All right. So this is kind of like the overall t-test. Again, curriculum goes through a lot more detail in this on like exactly how to proceed and how to do this. Any questions you guys might have? Any thoughts? So give me a thumbs up, sideways, downwards, how you feel about t-tests. Thumbs up like, yeah, I can do this all myself right now. Downwards like, I don't know where to even start. Sideways like, I get the concept, but I don't know if I can do it myself right now. And okay, that's okay. Because I think like this part right now, to be quite honest, is I haven't shown you guys how to do t-tests. So haha, right? Trick on you guys. None of you guys should be thumbs up. No, but I think this hopefully will give you guys an idea of like proceeding forward. Because in reality, performing a t-test is pretty easy. Like it's just a bunch of lines of code doing the same stuff over and over. But understanding what's going on is an important aspect of your actual statistical test. Okay, cool.